guys, welcome back. So what we're looking at today is lesson 12, systems of equations. So let's go ahead and jump right in. So system of equations is where we have more than one equation being represented on a graph, and when we're graphing them or solving them and working with them, we want to find their intersection point. So there's a hiking trail near the town where Han and Jada live that starts at a parking lot and ends at a lake. Han and Jada both decide to hike from the parking lot to the lake and back, but they start their hikes at different times. At the time Han reaches the lake and starts to turn back, Jada is 0.6 miles away from the parking lot and hiking at a constant speed of 3.2 miles per hour towards the lake. Han's distance d from the parking lot can be expressed as d equals negative 2.4t plus 4.8, where t represents the time in hours since he left the lake. What is an equation for Jada's distance from the parking lot as she heads towards the lake? So we know that she's going at a constant speed of 3.2 miles per hour. So that's her rate, that's her slope, so 3.2 t plus, and hers is 0.6 miles from the parking lot. So there is her equation. So now we're going to take and draw both graphs, one representing Han's equation right here, and the other one representing Jada's, to take and graph these out. So our two equations, we know that Jada's is going to start 0.246. Let me get this a little bigger. Okay, so there's Jada's starting point, and we know that she's going 3.2 meters per second. Not meters per second, miles per hour. Sorry. So we're going to go up and over. So we'd go up 3 total. So that's 0.6. There's 1. There's 2. There's 3. And over here to 1. Now, obviously, there's a big gap in here. So if we think about 3.2 and dividing it and cutting it into quarters, we would end up just going up 1, 2, 3, 4, and over 1, 2, 3, 4, and over 1, 2, 3, 4, and over 1, 2, 3, 4, and over. I think I got a little off in there somewhere. No. Yeah, that's right. Okay, so we could also keep extending this. So 1, 2, 3, 4, over 1, 2. There we go. So there is our line for Jada. Right? It's Jada? Yes. Okay. Now for our other one, for Han, is it? Yes. For Han, we'll do his in green. Now his equation is 4.8, so he's starting all the way up here, and he has a negative slope, so he's going down negative 2.4. So we go down, there's 1, there's 2, 3, 4, 2, 4. Okay. Then we'd go over all the way, to 1. Now, if we connect these, obviously my line is not perfect. Hang on, make that smaller. All right, connect these through. Now, obviously my line is very wobbly, but I did make sure to hit the intersection point. So these two lines intersect at 0.75 of an hour. So 3/4 of an hour. They meet at 3 miles. So find the point where the two graphs intersect each other. What are the coordinates? So where they're intersecting each other is at 0.753. So like I said, this is a system where we take and find that intersection. So system is your keyword for the lesson. All right, what do the coordinates mean in the situation? So what does the 0.753 mean? So it means 0.75 hours after Han left the lake, he passed Jada on the trail 3 miles from the parking lot. So it's taking into account all these different parts, all these things that go into this equation. The fact that they're distance from the parking lot, how much time, all of that is being represented when we explain what the coordinates mean in the situation. So being able to explain these things is very important. All right, what has to be true about the relationship between these coordinates and Jada's equation? So these values, these values make Jada's equation true. Now, what has to be true about the relationship between these coordinates and Han's equation? Same thing. These values make Han's equation true. That's the point of a solution. A solution is going to make the equation true, and the fact that it's the intersection between these two equations means it's making both the equations true. Now, if we were to plug the point 0.753 back into each of these equations and it didn't work for one of them, it didn't make it true, then we did something wrong in our graph. And so that's a really good way of double checking to see if you did something wrong, is by going back and plugging in that intersection point and working it out to see if it's true. All right, if you guys have any questions, feel free to ask. Have a great